Hi. This video I want to talk a bit about copulas. So this is another technique that's used often in Monte Carlo simulation. And we'll maybe go even a little faster on this one, but just give you some brief high-level comments on this. Perhaps you've heard this word before. And maybe I should put the ordering backwards here, but I think the key thing is it's an approach to simulate random variables from a joint distribution. It's an alternative to the Nataf or Rosenblatt. And it's used pretty often in finance, so that all these bankers that try to do a simulation of asset prices and things that are correlated, they use copulas a lot. It's used in hydrology as well. Rainfall at different points or flow through streams at different points and things like that. You've got these kind of dependent joint random variables, and copulas is a popular way for generating samples from them. So the idea is we're going to do something that looks like the inverse method but for joint distributions. So we've got a kind of a target joint CDF. We'll say we can generate samples from that thing if we go with the marginal CDFs for each xi. And then we've got this copula function. So look like the inverse method. If we've got an xi and we put it into its own CDF, we're going to get a number between 0 and 1. And then we map all those kind of 0, 1 dimensions through this copula function, and we can get out a joint CDF value. So these things are defined on the interval 0 to 1, but in n dimensions for the components that we want. All right. And there's this Schuyler's theorem that says for any joint distribution that's continuously differentiable, you can come up with a C function. So it's possible to work through the C function if you can drive it. All right. And that's enough here, I think. So a Gaussian copula is pretty straightforward. You could just use the multivariate Gaussian CDF to get through. There are some other ones of Gumbel distribution, things like that. There are also these things called empirical copulas where you can match an empirical distribution a little bit more flexibly and not specify a parameterized distribution. And a reference down at the bottom about some kind of details of those things. I think the key for us is just to say that there is this function that's a multivariate function that will map us through to a joint distribution that's got some sort of dependence. Okay? You can do the same type of thing here. So we could draw, if we want to do reliability analysis, we can draw samples yj from the copula. And this is similar to drawing z equals lu samples in the Nataf distribution. I'll call it the Nataf approach. So remember when we were trying to draw samples from that using the Nataf distribution, I'd draw independent samples, multiply normal distribution samples, pre-multiply them by that L matrix to introduce correlation and get the z's, and then we use the z's with our inverse method. So here the y's are playing the role of the z's. So we'll sample from this copula. It doesn't have to be a multivariate normal. It comes from some other type of distribution, but then we'll put those y's into the inverse marginal CDFs. So this is just an inverse method. And that will give us x's that have the correct marginal distribution. And because the y's came out of some sort of joint distribution, that'll introduce some dependence among the x's. Okay. And then we could take those x's, feed them into our limit state function, and compute probabilities of failure as before. Okay. Some strong similarities there to that Nataf approach, but we've got more flexibility in defining that copula function. So the few notes on this is it's really focused on generating samples from highly dependent variables. So if there's, especially in the extremes of the distribution, the very large or small values of x, if there's some sort of dependency structure, copulas are a nice way of trying to characterize that. And that's where they get used in applications a lot. If you can use one of these kind of clean families of copulas, so if you use a Gaussian copula or something like that, it's pretty straightforward to do this all. But characterizing that dependent structure is not necessarily easy. And the dependence is defined in that unit Q, the 0 to 1 intervals, rather than in the original random variable space. That's the kind of trick to these things, is getting how do you specify that dependent structure. So that's a quick overview in just a few minutes of this copulas. Again, we're not going to implement it in this class, but I wanted you to have some general awareness of it as it's kind of another one of the popular tools in Monte Carlo simulation. Okay.